A floating vane diffuser provides the potential to radically improve the performance of centrifugal compressors. But of perhaps greater importance is the demonstration of a feature that could be used to great advantage in a concept for self-starting gas turbine engines. This chart shows the origin, relationship, and potential benefits of the concepts. One U.S. patent on the floating vane diffuser itself led to the construction of a Lexan functional demonstration unit of the floating vane action. It in turn would lead to a compressor development program similar to any other compressor development program. The floating vane diffuser was also utilized as a check valve in a self-starting gas turbine engine patent, whereas the floating vane diffuser was the best embodiment of that check valve. This in turn would lead to a self-start analysis and experimentation with an actual engine. At the conclusion of that, perhaps the results of the compressor development program could be utilized to even better advantage in the self-starting engine. As a result of the self-starting engine, we would end up and have an improved cold start function of a jet fuel starter or an APU, a substantial weight reduction, and perhaps improvements in altitude start and altitude operation. At the conclusion of the compressor surge program, or the compressor development program, we would have an improved conventional compressor which could be used in a conventional Brayton cycle engine. As an introduction to the self-start concept, let's compare a ramjet to a pulse jet. The pulse jet being like that of the German V-1 buzz bomb of World War II. This chart compares the ramjet to the pulse jet, where fundamentally the only difference is that the pulse jet has a set of flapper valves and it will start and provide useful thrust at velocity of 0, whereas the ramjet requires a starting power or a velocity before it can be started and provide useful thrust. Going in the other direction of the matrix, the ramjet, if we simply add a compressor and a turbine to it, we have a Brayton cycle shaft engine still requiring the external start power. If we add a compressor and a turbine to the pulse jet, still retaining the flapper valve feature, we should be able to have an engine which requires 0 start power and which will provide useful shaft horsepower to accomplish that starting function. This then is the fundamental idea of the self-start concept. We have the basic compressor and turbine of the Brayton cycle engine. We have a combustor here. We make the addition of a check valve between the compressor and the combustor with fuel and ignition with periodic pulses of fuel added and ignited. The pressure rises. It does not go forward through the compressor. We obtain useful pressure and turbine inlet temperature to drive the turbine, which in turn accelerates the shaft since the compressor is minimally loaded at that pulse. It would, in theory, be no external starting power. Rotor speed would essentially ratchet up. We would pulse fuel, turn it off, let it coast down and get a recharge of fresh air from the compressor, pulse another burst of fuel, let the compressor pull in another charge of fresh air, and so forth until we reach 100% speed. And this should be at least as fast or perhaps faster than the conventional linear rise in rotor speed of a Brayton cycle engine. Now we'll move on to the floating vane diffuser. Let's keep in mind the flapper valve function introduced in the self-start concept. This chart shows a typical diffuser or vane arrangement of a centrifugal compressor. The conventional diffuser with the impeller here provides outwardly radial diffusing channels. The floating vane diffuser basically still provides that channel, but it takes the forward edge of the diffuser vanes and puts in a movable set of diffuser vanes which close as flow is reduced or back pressured in the compressor itself. And these vanes are free to move about an axis well forward of any center of pressure or lift on the vanes. Ideally, it's at the very leading edge. The floating vane diffuser should provide a substantial improvement in the surge margin of a conventional compressor. In this region, just shown as typically. This is a compressor map, which shows pressure and flow with lines of constant speed as they go up to a conventional surge margin. With the floating vanes, we would expect this surge margin to improve over into at least this region and perhaps even further. This demonstration unit presently has a conventional fixed one-piece diffuser vane arrangement installed. The rig overall consists of an electric motor driving a 5-inch diameter bladed impeller. Ambient air enters the impeller through the inlet, then exits the impeller into the diffuser vane channels, then dumps into a large plenum, then out through a throttle valve. The throttle valve is a movable plate over a hole in the sidewall. The unit has all the basic elements of a centrifugal compressor as used in turbochargers, refrigeration units, and gas turbine engines, particularly APUs, jet fuel starters, small missile propulsion engines, and even some manned aircraft propulsion engines. Even though this model operates at a relatively low speed and pressure ratio, it sufficiently exhibits a surge, or reverse flow, condition in the diffuser channels. Surge is an undesirable characteristic of high-performance compressors, which designers and users are both well aware. It could be argued that only stall is being demonstrated. Even so, stall is closely associated with surge, so that what affects one would probably affect the other. The electric motor is of the universal type and does not maintain constant speed independent of load. The lower the load, the higher the speed. Therefore, in relation to a typical compressor performance map, we will be approaching and entering the surge regime in a manner shown on this typical map. We have our basic map with still our flow and pressure ordinates and abscissa, the lines of constant speed with a surge margin wherever it will be. It will be a fixed value in the case of the conventional compressor. We will start off at full flow, minimum pressure, increase the back pressure, and as we come up in pressure and decrease in flow, we will increase in speed and proceed across a relatively flat pressure zone towards the minimum flow. Most investigators agree that the surge, or periodic reverse flow, is triggered by adverse flow incidents on the impeller blading or the diffuser vanes. The surge phenomenon to be observed in this demonstrator is clearly associated with the incidents on the diffuser vanes. Some other features of the rig are air inlet duct, a plenum pressure gauge in inches of water, flow visualization streamers in the diffuser channels at mid-channel height. Watch for these streamers to reverse direction when flow pulsations are heard. We will now operate the demonstrator rig, beginning with the throttle valve open and slowly close it towards the surge regime, increasing pressure as we go. We will now remove the conventional vanes and install the two-piece floating vanes. We will now operate the rig with the floating vanes. With higher airflow, the two-piece configuration behaves like the previous one-piece demonstration unit. There is flutter of the vanes. Notice also that the vanes go towards a closed position as the flow is decreased. There is lessened reverse flow, as evidenced by the streamers. There are reduced pulsations on the pressure gauge. And during the rapid operation, the flapper valve function is demonstrated very readily. You probably noticed that not all of the vanes were in identical positions for intermediate flows, even though they are fully close on each other for the zero flow condition. There would most likely be an improvement in synchronized movement with a more precisely constructed set of vanes, or if the vanes were linked together through a mechanism external to the flow stream. However, there need be no external actuator in any case, since the vanes move automatically. Not only do the floating vanes act as flapper valves, but they do so at a location that minimizes the impeller aerodynamic loading during shutoff. They will virtually eliminate any destructive coupling between the impeller blades and diffuser vanes. A smooth, continuous boundary ring is established at the impeller exit. Recirculation and heating will still take place in the impeller. This means that shutoff cannot be maintained very long without damage to the impeller. But the even more dangerous reverse flow shocks and blade-to-vane interactions are virtually eliminated. It is obvious that such a simple model cannot demonstrate the actual workings of a self-starting gas turbine engine. An actual system involves fuel injection, ignition, timing, high pressure, and temperatures. The complete validation of the self-starting concept will require reconfiguration and experimentation on an actual engine. In summary, we have the unique situation of two concepts that can be considered separately or together. The self-start concept, with or without use of the floating vanes, can eliminate the conventional starter and its gearing to radically reduce the installed weight and size of small gas turbine engines. The floating vane concept, whether used in the self-start concept or not, has the promise of improving the surge margin and efficiency of a centrifugal compressor. Clearly, some research and development activity is warranted to determine the feasibility and applicability of either or both of these concepts. R&D program decisions should consider including these concepts for further validation and characterization.